Hello, and welcome to the Applied Statistics Using Programming lecture series. This video is Lesson 6, where we discuss continuous distributions. The goal of today's lesson is to better understand what are continuous distributions, how can they be used, and to practice using R programming, how we can use these tools. All right, so let's get started. Continuous probability distributions. Today, we're going to cover the uniform distribution, the normal distribution, and the standard normal distribution in detail, and we'll mention briefly about the exponential distribution towards the end. All right, first, let's discuss a bit about what are continuous probability distributions. A continuous probability distribution is different than a discrete probability distribution. If you remember from lesson 5, a discrete probability distribution has a countable number of outcomes. However, a continuous probability distribution has an infinite number or a continuous number of outcomes, and therefore we need to adjust our understanding of how that distribution works. When x is a continuous variable, for example, waiting time, it doesn't make sense to speak of probability at a particular value. For example, it doesn't make sense to use x equals 54 seconds. Why? Because it could be 54.1 or 54.0000001 because the values of x are not a set of discrete points. It's a continuous variable. Probabilities for continuous variables are defined as areas under a curve called the probability density function, or the PDF. Probabilities for a continuous random variable are also defined on intervals, such as the probability of waiting between 53.5 seconds and 54.5 seconds, or the probability of waiting less than 54 seconds, or the probability of waiting equal to or more than 53 seconds. In other words, instead of discussing probabilities at a specific point, because there are infinite points, we discuss the probabilities of a range of points when using a continuous probability distribution. So a PDF, or a probability density function, is denoted by f of x, a function of x. It must be non-negative, and the total area under the curve is 1 or 100%. The mean, the variance, and shape depend on the PDF parameters, the parameters of the distribution. It reveals the shape of the distribution. An example is the normal PDF, which is shown right here. Sometimes this is called the normal curve. Technically, it is a probability density function. Similarly, as we learned in lesson 5, the continuous CDF refers to the cumulative proportion of our x value. It's useful for finding probabilities, and an example is the normal CDF, which is shown right here. So a little bit differently than the discrete distribution, a continuous probability distribution, we talk about the area under the curve, which looks like this. So in this example, we're looking at the area under the curve between points A and point B, and this area under the curve has a probability. Unlike discrete distributions, the probability at any single point equals 0. The entire area under the PDF, by definition, is set to 1, or 100%. The mean is the balance point of the distribution. All right, so first, let's talk about the simplest distribution, which is the continuous uniform distribution. What a continuous uniform distribution means is any value in our distribution has the same probability of occurring. So if x is a random variable that is uniformly distributed between A and B, its PDF has a constant height because all values are equally probable. So we can denote this as U, A, B. The parameters that we need are just A and B. A is the lower limit, B is the upper limit. If we know A and B, we know the probability of any value between them is equally likely. Next, let's talk about the normal distribution. The normal distribution is probably one of the most important distributions in statistics. The normal, or Gaussian, or bell-shaped distribution was named for German mathematician Carl Gauss. The normal distribution is defined by two parameters, mu, the mean, and sigma, the standard deviation. We denote the normal distribution by n, meaning normal, mu, and sigma. These are the only two parameters that we need to be able to describe our normal distribution. The population mean, mu, and the population standard deviation, sigma. The domain, in other words, the range of values that x can have on a continuous scale are between negative infinite and positive infinite. In other words, our x continuous variable can have any value infinitely positive or infinitely negative. However, almost all, about 99.7% of the area under the curve is within the range of 3 standard deviations above and below the mean. So nearly all of the data falls between 3 standard deviations above and below the average. The distribution is symmetric, meaning equal on both sides, and unimodal, meaning we have one peak in our distribution. Now, a normal distribution looks like this, a bell shape. And as we see, the middle of the bell shape is our mu, the mean of our population. It's important to understand that all normal distributions have the same shape, but they may differ in the axis scales. Why? Because the mu, or the standard deviation of different random variables, will have a different average and a different standard deviation. But given the mean and standard deviation, they all have this same shape. So a normal CDF has this kind of an S curve to it. It approaches but never reaches 1. So why does this CDF never actually reach 100%? Because, as we remember, the domain ranges from negative infinity to positive infinity. Okay, what is normal? Many physical measurements in the real world resemble a normal distribution. We mentioned several of these in a previous video. To be regarded as a candidate for normality, in other words, if we think that it might be normal, that random variable should be measured on a continuous scale, possess a clear center of the data, have only one peak in the distribution, have tails that taper, they get smaller, and be symmetric about the mean. That means that each tail should be roughly equal. When the range is very large, we often treat a discrete variable as continuous. For example, exam scores are discrete. They range from 0 to 100, but we often treat exam scores as continuous data. Here are some examples of random variables that might be expected to be approximately normally distributed. The first example is very specific. I'm not sure why. X equals the quantity of beverage in a 2-liter bottle of Diet Pepsi. Doesn't need to be Diet Pepsi. It could be the amount of ice cream in a pint of ice cream, or the amount of water in a water bottle, for example. What this means is, if we measure it very precisely, we might expect there should be 2 liters in your Diet Pepsi, but it might be slightly more, slightly less. And if we calculate all of the Diet Pepsi coming out of the Pepsi manufacturing plant, we could probably measure that it follows a normal distribution around the average of 2 liters, Sometimes it's a little bit more, sometimes it's a little bit less. The distribution, if we measured all of the Pepsi 2-liter bottles coming out of the plant, would follow a normal distribution, around that mean of 2 liters. Another example is the noise level in a Boeing 777. In other words, the airplane makes a lot of noise, but that noise decibel level will also follow a normal distribution. Sometimes it's a little bit louder, sometimes it's a little bit less. Finally, the last example is the diameter in millimeters of a manufactured steel ball bearing. Most of these examples are about manufacturing, right? When we're manufacturing, we have an expectation of what that size should be. However, machinery is not perfect, so sometimes it will be exactly the millimeter that it should be. Sometimes it'll be a little bit more, sometimes it'll be a little bit less, but it will follow a normal distribution. It's very unlikely to be a lot more or a lot less when you're manufacturing a specific size. All right, so what is a standard normal distribution? If all of these many different random continuous variables can follow a normal distribution, well, if we know the mean and the standard deviation, we can adjust this to create a z-score, as we showed in a previous video. Since for every value of mu and sigma, there's a different normal distribution, we can transform a normal random variable to a standard normal distribution with mu equals 0 and sigma equals 1 using the formula xi for every value that we have, xi, minus the average over the standard deviation. That's how we get a z-score. A z-score is just a transformed value of the variable that represents how many standard deviations above or below the mean. All right, so this is just the same as a normal distribution where mu is 0 and sigma is 1. So what are the characteristics of a standard normal distribution? Well, the mu, the mean, is 0 and the sigma is 1. So if we look at a PDF of a standard normal distribution, we see that the mu is 0 and 1 standard deviation above the mean would be just 1. 2 standard deviations above the mean would be 2. 1 standard deviation below the mean would be -1. Why? Because each standard deviation is transformed to be 1. It makes it very easy to compare z-scores because it tells us how many standard deviations above or below the mean that value is. So a standard normal distribution is much easier because it's been standardized and we can directly compare z-scores between distributions. The characteristics of a normal CDF looks similar, and we see that the middle value is just 0. So why is the standard normal distribution so useful? The same as any normal distribution, approximately 68% of the area under the curve is between 1 standard deviation. But because we standardized it, 1 standard deviation is just +1. 1 standard deviation below the mean is just -1. So between -1 and 1, we have 68% of the area under the curve, as shown in this very small example here. Between -2 and +2, we have about 95% of our values, and between -3 and +3, we have 99.7%. Almost all of our data should fall between -3 and +3 standard deviations. So since the normal distribution is symmetric, we can also make some calculations about specific probabilities. So if I wanted to know 95% of my data falls within a specific range, that means that using a normal distribution, we can use the z-scores -1.96 and +1.96. That gives us 95% of our data. This means that 5% of our data is outside of this range. This will become important later when we start talking about hypotheses testing. So from any point in this normal distribution, we can calculate the probability of the area under the curve. As long as we know mu and sigma, we can calculate any values under our normal distribution. In a standard normal distribution, we already know what that mu and sigma are. What are they? Mu is 0 and sigma is 1. That makes it very easy to calculate on this standard normal distribution. All right, so as we see on the left side, we have a normal distribution. How do we know it's normal distribution? Well, it follows that same curve. And in this case, the mu is 75. Let's say this is the height of people. The average height of people is, let's say, about 75 centimeters. And plus or minus 7. So minus 7 would be 68, plus 7 would be 82. So our standard deviation here would be 7. If we transform this same data, the height of people, into a standard scale, well, the average becomes 0, and the standard deviation becomes 1. So what does 0 mean? This 0 means 75. But on a standard normal distribution, we can calculate, instead of using our x value, we can use our z value, our z-score. The distribution is exactly the same. We're just converting it to this standardized scale, and that allows us to compare it with other standardized normal distributions. So other continuous distributions include normal approximations of the binomial and Poisson distributions. Binomial and Poisson distributions we learned in lesson 5, which was about discrete continuous distributions. If we have a very large number, they approximate a normal distribution. When there are a large number of trials, the binomial distribution approaches a normal distribution. So the binomial distribution can be approximated using a normal distribution. The exponential distribution is different from the normal distribution. If events per unit of time follow a Poisson distribution, the time until the next event follows the exponential distribution. Think of it like this. Let's say that you're driving your car and you arrive at a red light. How much time does it take before that light turns green? The longer you wait, the more likely it's going to turn green sooner and sooner. This characteristic follows an exponential distribution, the time you're waiting until that light turns green. The triangular distribution is a very basic distribution that is shaped like a triangle. The peak of the triangle would be the most likely value, where the other points of that triangle would be the maximum and minimum value. This can be used in, for example, consulting if we're looking at a what-if analysis. So if we don't know much about the business case, we might have a general idea of the maximum value or the minimum value and the most likely. In that case, we can use a triangular distribution. All right, let's start the R session for lesson 6. All right, so continuous probability distributions. Set seed, if you remember from last time, will give us the same random result every time we use this function. This function here, RUnif, standing for random uniform distribution, and the 1 indicates that I'm asking for one random value from the uniform distribution. So let's see what random value we get. Okay, we got 0.55. Some very long number. Why? Because this is continuous. It can be any value between 0 and 1. All right, so if I wanted to get a more predictable value, I could set my seed first. Let's clear our console. I'm going to run this code where we set our seed and then sample one random value from the uniform distribution. We get 0.2655. If I do it again, because I'm setting the seed, every time I run this code, I'm getting the same value. So setting the seed will give you a predictable random value. Now, it doesn't matter what number we use here. It's very common to use the number 42
Many millions of years ago, a race of hyper-intelligent, pan-dimensional beings got so fed up with the constant bickering about the meaning of life that they commissioned two of their brightest and best to design and build a stupendous supercomputer to calculate the answer to life, the universe, and everything.
The answer to the ultimate question of life, the universe, and everything is 42.
We'll get a different random number, but every time we run it, we'll get that same random number as long as we're setting the seed first. Okay. So when I set my seed to 1 and use this random uniform function, I get 0.2655. Well, what if I took this number, copy it, paste it, and I said, is the result equal to this number? Let's check. If you read my note, you already know that it is false. Okay, so the proper way to do this would be to use a range. So for example, our random uniform value is 0.26, but if we use, is this number less than 0.5? Yes, of course. So we should use a range because the number that we're actually sampling is infinitely long. So we can make a more specific range using two values. So for example, is our random value between 0.25 and less than 0.75? Yes, that would be true. So let's look at the continuous uniform distribution. To use the uniform distribution, we can use this function here. So let's take a quick look at how this function works. Let's use the question mark for the help menu, DUNIF. All right, so this is the uniform distribution. And there are several related functions here. In this case, we're using our D uniform distribution. Okay, so when using the D uniform distribution, 0 is the minimum, 1 is the maximum. We can change these arguments if we want to select a uniform distribution between 2 points, and x is the values that we're looking for. So in my function, I'm setting minimum to 0, maximum to 100. Because it's a continuous distribution, there are an infinite number of values between 0 and 100. So what is the probability of getting 50 in that range? We get 0.01, like 1%. That doesn't make any sense, does it? Because any specific value in your continuous variable, the probability of having that specific value, let's say 50, should be 0. But it's not very useful if the probability is 0, so instead we can use what's called a probability density. So if we drew a curve, because this is a uniform distribution, our curve just looks like a square. So let's take a look. If we plotted all values from 0 to 100, from 0 to 100, it just looks like a square, right? Our histogram suddenly just looks like a square with all the values between 0 and 100. If we bring that out, you'll see that we get all those values here. All right, and at all of those points, it's a 0.01. This is the probability density. In other words, any value that we choose between 0 and 100 is going to have the probability density of 0.01. So if that's true, what if we change this number to a different number? We would get 0.01. Let's say we change it to 2, 0.01. Actually, any value between 0 and 100, we're going to get that probability density. All right, so let's test that. What if I use the number 0.1? We get the same result. What if I get the number 0.01 or 0.000001? This is still between 0 and 100. It gives me the same probability density. Let's look at our cumulative distribution function. Let's say 50, we get 0.5 because this is right in the middle between 0 and 100. Well, let's try a different number. Let's say we use 1. We get the probability 0.01, 2, 0.02. All right, so now this is starting to make a little sense. Let's graph that. And we get the result for every increase of 1 between 0 and 100, our cumulative probability increases by 0.01. All right, so that's how we can use this uniform distribution. Okay, let's look at the normal distribution. This set seed is going to give me a predictable result. So your results will look the same as my results if we run this set seed, because this function here will select a random number, r, from the normal distribution. And I'm asking to create 1 million random numbers from a normal distribution, and that normal distribution has a mean of 100 and a standard deviation of 15. If we look at IQ scores, the average IQ score is 100, and the standard deviation of those scores is 15. Okay, so this function here is simulating choosing 1 million random people's IQ scores with a mean of 100 and a standard deviation of 15. What this function is doing is generating 1 million IQ scores, mean of 100, standard deviation 15, which follows a normal distribution. So let's look at this function here, dnorm. So Einstein is reported to have an IQ score of 160. So this function is saying, what is the probability or the relative probability, using the probability density function, of a specific value occurring? Of specifically, what is the probability of having an IQ of 160 when the average of IQ scores is 100 and the standard deviation is 15? That gives us 8.9 error minus 6. In other words, a small number, a number with 5 zeros in front of it, 0.00008. So let's look at what that would look like on a normal distribution curve. So this is a normal distribution. We can plot it using curve dnorm, so it'll make a normal distribution. And it's from -3 to 3, so this is a standard normal distribution. How do we know it's a standard normal distribution? Because the mu is 0 and each standard deviation is 1. So let's draw a histogram of x. What was x? X was the 1 million random values that were generated using the normal distribution. So let's look at what happens when we make a histogram. It follows that same pattern. And let's draw a line on our histogram to show the probability density. This density function is creating the probability density of our random variable x. So what that does is it draws a actual probability density, which looks almost exactly like that theoretical normal distribution curve. All right, so let's look at that sample of 1 million IQ scores. It looks almost the same, and we'll draw a line at 160 on that distribution. All right, so this is an example of IQ scores. The average is 100. We sampled or generated 1 million IQ scores with an average of 100. And some are above it, some are below it. And what we see is if we had 1 million people, what is the probability of having this IQ score of 160? The probability is this number here, 0.00008. The probability of being the individual at this point in our curve is this number right here. Let's look at a CDF. We can draw that curve using the normal distribution. This is going to show us a CDF of the normal distribution. This is the theoretically perfect CDF of a normal distribution. So let's say, using IQ scores again, because those follow a normal distribution, and we know the mean and we know the standard deviation of IQ scores. So the US military officially has a minimum requirement of 80 IQ or higher. Now, I'm not sure if they still do this, but I believe so. So let's check. How many people have an IQ score of 80 or lower? About 9%, almost 10% of the population has an IQ score of 80 or lower, right? So using this p-norm function, we can check a more realistic example of applying our normal distribution to a real-life situation. This tells us about 9% of the population has an IQ of 80 or lower. Now let's look at the other end of that distribution. If we're looking at a normal distribution and the top tail of that distribution, we can change our function to say lower tail equals false, meaning not on the lower end of the distribution, but on the higher end of the distribution. What is the probability of having an IQ of 130 or higher, given a mean of 100 and a standard deviation of 15? That gives us the result, about 2%. So how can we interpret this result? Well, let's say, for example, that you are on a subway with 100 random people. Based on the normal distribution, about 2 of those people in a subway car with a random 100 people on it, about 2 of them would qualify to be in the Mensa. Let's look at an example of a standard normal distribution. Let's say we make those 1 million IQ scores again, randomly from a normal distribution, mean 100, standard deviation 15. We can transform that data into a standard normal distribution by taking our x values minus the mean, which is 100, divided by the standard deviation 15. That will give us our standardized normal distribution. So let's plot a histogram of our standard normal distribution. That looks exactly the same as our normal distribution, only instead of an average of 100, we have the average of 0. All right, so let's also standardize Einstein's IQ. As we said before, Einstein's IQ is 160. So how would we standardize that? We would take 160 minus the average divided by 15. That gives us a z-score. In other words, Einstein's IQ is 4 standard deviations above the average population. So we can also look at the probability of that occurring, which is 0.0001. All right. In other words, it is very unlikely to find a person with a similar IQ to Einstein.
All right, I'm editing this video and I don't really like my explanation here. The reason is that a probability density is not the same as a probability. A probability density describes the probability per unit of x. So in other words, if we change the scale of x, then our probability density will also change. So in our first example, when we use our normal distribution, we get 0.00 something 8. And then when we change that into a z-score and we use the same function, although the location on the distribution hasn't changed, that y-axis of the probability density is a little bit different because the scale of x, when we're using the normal distribution or after we standardize it, that scale is different. So it results in a slightly different probability density. So in continuous probability distributions, we're using a probability density when we're looking at that d-norm function, because the d-norm function is telling us at that one specific point. That's why it's much more common to use p-norm or to extract the p-value or use an area under the curve because it's much more intuitive than a probability density when we're just looking at that line rather than the area under the curve. So I usually recommend to students to focus and to use the area under the curve rather than using the probability density because it can be a little bit confusing, especially if you're new to statistics. Cool, back to the video.
All right, so let's look at that same CDF. Let's transform that into our standard normal distribution. We get the same result, but you can see we used the function with a mean of 0, standard deviation of 1, and we changed our value 80 into the z-score with that distribution. In other words, we can use the same function using a mean of 0 and a standard deviation of 1. If we transform that value into a z-score, it will give us the same result. And we can do the same thing with that Mensa score. We'll get the same value that we did before, using a standard normal distribution instead of a normal distribution. All right, that's it for our R code for today. Thank you for watching. This concludes lesson 6 of our Applied Statistics Using Programming series. I hope you'll join us in the next video. Thank you, and see you soon. This is an AI picture. It's not the best. Don't look too closely at the picture. It stops making sense if you look too closely. When we're talking about a continuous CDF, we're using the cumulative. There we go. BCAM.